Welcome to Sleeping Researcher, your peaceful space for science narration designed to help you relax and drift gently into sleep. Tonight, we will explore the fascinating world of superconductors, remarkable materials that challenge our understanding of electricity and magnetism. Superconductors are unique substances that, under certain conditions, conduct electricity without any resistance. This near-magical property has captured the imagination of scientists and engineers for decades. Imagine power flowing effortlessly through wires, or magnets levitating without friction. These are just glimpses of what superconductors make possible. In this narration, we will gently journey through both the theoretical wonders and the practical applications of superconductors, from the promise of lossless power grids to the marvels of magnetic levitation trains, and even the potential to revolutionize medical imaging. Superconductors hold a key to future technologies that could transform our daily lives. We will explore how these materials work, the challenges they face, and the exciting research paving the way for new breakthroughs. If you find this exploration as intriguing and calming as we hope, please consider liking this video and subscribing to Sleeping Researcher. Your support helps us continue sharing soothing science stories designed to relax your mind and enrich your curiosity. Now, settle in as we begin our tranquil dive into the extraordinary world of superconductors. Imagine a world where electricity flows without resistance, where energy is transmitted flawlessly, and where magnetic fields are manipulated with ease. This is the promise held by superconductors, remarkable materials that, under certain conditions, exhibit zero electrical resistance and expel magnetic fields. Discovered in the early 20th century, superconductors have since captivated scientists and engineers alike, sparking a continuous quest to understand their underlying physics and harness their extraordinary properties. These materials defy the conventional rules of electrical conduction, offering a glimpse into a future where energy loss becomes a relic of the past. Their unique behavior arises when cooled below a critical temperature, enabling electrons to pair up and move coherently through the lattice structure without scattering. This phenomenon opens doors not only to theoretical exploration, but also to practical applications that could reshape multiple industries. The theoretical uses of superconductors extend far beyond simple electricity conduction. In physics, they enable the creation of powerful electromagnets with minimal energy input, which are essential in particle accelerators and magnetic resonance imaging devices. Additionally, superconductors are key to the development of quantum computers, where their ability to maintain coherent quantum states facilitates faster and more efficient computation than traditional semiconductors. Researchers also envision their role in energy storage systems, such as superconducting magnetic energy storage, which can store and release electricity rapidly and with minimal loss. The potential for superconductors to revolutionize these fields is immense, yet it hinges on overcoming practical challenges, such as the need for extremely low operating temperatures and the brittleness of many superconducting materials. Nevertheless, ongoing advancements in material science continue to push these boundaries, bringing theoretical applications closer to reality. In practical terms, superconductors have already begun to leave their mark across various sectors, One of the most notable applications is in magnetic levitation trains, or maglevs, which use superconducting magnets to lift and propel trains with minimal friction, enabling unprecedented speeds and energy efficiency. In medicine, superconducting magnets are integral to MRI machines, providing strong, stable magnetic fields that produce detailed images of the human body without invasive procedures. Power grids are also exploring superconducting cables that can transmit electricity over long distances without loss, potentially leading to more reliable and sustainable energy distribution networks. These applications highlight how superconductors translate complex quantum phenomena into tangible benefits for society. Yet, the journey toward widespread adoption remains ongoing as scientists work to discover materials that operate at higher temperatures and integrate seamlessly into existing technologies. Understanding superconductors thus opens the door to revolutionary technologies that could transform energy, transportation, and computing. The interplay between their fundamental physics and practical potential continues to inspire a wide array of research, from developing new materials to engineering innovative devices. Each step forward brings us closer to a future where the limitations of resistance and energy loss are overcome, enabling cleaner, faster, and more efficient systems. As this exploration progresses, it invites us to consider how such breakthroughs could reshape daily life, industry, and scientific discovery itself. With these ideas in mind, we can now delve deeper into the fascinating physics behind superconductivity and the challenges faced in bringing these materials from the laboratory into everyday use. At its core, a superconductor is a material that can conduct electricity with absolutely no resistance when cooled below a certain critical temperature. This means that an electric current can flow indefinitely without losing any energy as heat, a stark contrast to ordinary conductors, such as copper or aluminum, where resistance causes energy loss and limits efficiency. The phenomenon of superconductivity was first discovered in 1911 by Heike Kamerlingh-Onnes, who observed that mercury, when cooled near absolute zero, suddenly displayed zero electrical resistance. This discovery challenged the classical understanding of electricity and materials, opening a new realm of physics to explore. Superconductors are not only defined by their zero resistance, but also by their ability to expel magnetic fields, a property called the Meissner effect, which allows them to levitate magnets or be levitated themselves. This unique interplay between electrical and magnetic properties places superconductors at the frontier of condensed matter physics, where quantum mechanics governs the behavior of electrons in ways that defy everyday intuition. Understanding these fundamental characteristics helps us grasp how materials can conduct electricity without resistance, an extraordinary physical phenomenon that continues to inspire scientists and engineers alike. The theoretical underpinnings of superconductivity rest on the formation of Cooper pairs of electrons that move through a lattice structure in a coordinated fashion, avoiding the usual scattering that causes resistance. This pairing occurs due to subtle interactions with the vibrations of the material's atomic lattice, known as phonons. The BCS theory, named after Bardeen, Cooper, and Schrieffer, elegantly explains this behavior for conventional superconductors operating at very low temperatures. Yet the story becomes more complex when considering high-temperature superconductors discovered in the 1980s, which function at temperatures significantly higher than previously thought possible. These materials, often copper oxide ceramics, defy a full theoretical explanation, prompting ongoing research into unconventional mechanisms that could enable superconductivity at or near room temperature. Such advancements hold profound implications, for if we can understand and harness these materials fully, the practical applications could revolutionize how we generate, transmit, and utilize electrical energy. The pursuit of room temperature superconductors remains one of the most exciting and challenging frontiers in modern physics. Practical applications of superconductors are already visible in several cutting-edge technologies. In medical imaging, superconducting magnets are the cornerstone of magnetic resonance imaging, MRI machines, providing powerful and stable magnetic fields essential for high-resolution images of the human body. In transportation, maglev trains leverage superconducting magnets to achieve frictionless motion, enabling quiet, fast, and efficient travel by floating above the tracks. In the realm of energy, superconductors promise to transform power grids by enabling lossless transmission lines, reducing waste, and improving the stability of electricity supply. Moreover, superconducting materials are critical in particle accelerators and experimental fusion reactors, where strong magnetic fields and minimal energy loss are vital. While these technologies already demonstrate the potential of superconductors, broader adoption is often limited by the need for extremely low operating temperatures and the cost of cooling systems. Nonetheless, as advances in material science and cryogenics continue, the scope of practical uses expands steadily, slowly bringing these extraordinary materials closer to everyday applications. Each new innovation builds on the remarkable properties of superconductors, hinting at a future where their unique capabilities reshape numerous fields. Beyond the tangible applications, superconductors hold promise in the emerging field of quantum computing, where their ability to maintain coherent quantum states with minimal energy loss is invaluable. Superconducting qubits, the fundamental units of quantum information, rely on these materials to achieve the delicate balance between quantum coherence and controllability. By minimizing electrical resistance and environmental interference, superconductors help sustain the fragile quantum states necessary for computation, far beyond the capabilities of classical computers. This potential could revolutionize problem-solving in cryptography, material design, and complex simulations across various scientific disciplines. Additionally, superconductors contribute to the development of ultra-sensitive sensors, capable of detecting minute magnetic fields or gravitational waves, further expanding our ability to observe and understand the universe. These advances underscore the profound impact that mastering superconductivity may have, not only in technology, but also in fundamental science. As researchers continue to unlock the secrets of these remarkable materials, the horizon of possibilities broadens, inviting us to imagine new realms of innovation and discovery. However, the journey from laboratory curiosity to widespread practical use is marked by challenges. The need to maintain extremely low temperatures, often using liquid helium or nitrogen, imposes significant technical and economic constraints. Many superconductors are brittle or difficult to manufacture into useful forms, such as wires or tapes, limiting their integration into existing infrastructure. Researchers are actively exploring novel materials, including iron-based superconductors and engineered nanostructures, to overcome these hurdles by increasing critical temperatures and improving mechanical properties. Advances in cryogenic technology and cooling methods also play a crucial role in making superconducting devices more accessible and cost-effective. These ongoing efforts reflect a dynamic interplay between fundamental physics, material science, and engineering, driven by the vision of a world where superconductivity is no longer confined to specialized environments, but becomes a cornerstone of modern technology. As we continue to explore how superconductors can be tamed and tailored for the future, we draw ever closer to realizing their full potential across diverse domains. In the early 20th century, the landscape of physics was ripe with curiosity and exploration. It was in 1911 that the Dutch physicist Heike Kamerlingh-Onnes made a discovery that would forever alter our understanding of electrical conduction. While investigating the resistance of metals at temperatures approaching absolute zero, Onnes observed a startling phenomenon in mercury. Its electrical resistance abruptly vanished below a certain critical temperature. This unexpected behavior defied the prevailing theories of the time, as materials were believed to simply exhibit decreasing resistance with temperature, but never a complete loss. The term superconductivity was born to describe this remarkable state where electrical current can flow indefinitely without energy loss. This discovery sparked a profound scientific fascination, inviting researchers to unravel the mysteries of quantum mechanics and condensed matter physics embedded within this new realm. The revelation that electrons could travel unimpeded through a lattice challenged existing models and laid the foundation for a rich field of inquiry that would span decades, inspiring both theoretical and experimental investigation. Following Kamerlingh-Onnes's initial observation, the scientific community embarked on a journey to characterize and understand superconductivity more deeply. Theoretical frameworks such as the BCS theory, developed in the 1950s, provided a quantum mechanical explanation for the formation of Cooper pairs, pairs of electrons bound together at low temperatures that move through a material without resistance. This insight not only demystified the phenomenon, but also opened the door to envisioning practical applications rooted in the unique properties of superconductors. The ability to conduct electricity without dissipation suggested revolutionary possibilities for energy transmission, promising vastly improved efficiency compared to conventional conductors. Moreover, the magnetic properties of superconductors, notably the Meissner effect, where magnetic fields are expelled from the material, suggested new ways to manipulate magnetic fields with precision. These theoretical advances have since guided material scientists and engineers toward harnessing superconductivity in innovative devices and systems. The elegant interplay between theory and experiment continues to propel the field forward as researchers seek materials with higher critical temperatures and more practical operating conditions. Practical applications of superconductors have gradually emerged as scientists and engineers learn to navigate the challenges of working at cryogenic temperatures and fabricating suitable materials. Today, superconductors play a vital role in technologies such as magnetic resonance imaging, or MRI, where powerful and stable magnetic fields are essential for detailed medical imaging. Particle accelerators also rely on superconducting magnets to steer and focus high-energy particle beams, enabling groundbreaking research in fundamental physics. In the realm of energy, superconducting cables offer the promise of lossless power transmission, although widespread adoption is limited by cooling requirements and material costs. Additionally, superconducting quantum interference devices, or SQUIDs, exploit the sensitivity of superconductors to magnetic fields, finding use in geophysics, medicine, and materials science. These applications illustrate how the peculiar qualities of superconductors can be translated into practical tools, even as the quest continues to discover materials that operate at higher temperatures and greater ease. Beyond these established uses, the promise of superconductivity extends into emerging technologies that could redefine computing, transportation, and energy storage. Quantum computing, for instance, leverages superconducting circuits to create qubits that maintain coherence far longer than traditional systems, offering a pathway to exponentially greater computational power. Magnetic levitation trains, or maglev, utilize superconducting magnets to achieve frictionless high-speed travel, hinting at a future of efficient and environmentally friendly transportation. In energy storage, superconducting magnetic energy storage systems, or SMES, store electricity in magnetic fields with minimal losses, providing rapid response and stability to electrical grids. Each of these prospective applications depends on continued advances in materials science and engineering to overcome the practical limitations of current superconductors. The ongoing evolution of superconductivity research is a testament to human ingenuity, fueled by the vision first sparked by Kamerlingh Onnes's discovery over a century ago. One of the most fascinating phenomena in physics is the complete absence of electrical resistance in certain materials when cooled below a critical temperature. This phenomenon, known as superconductivity, was first observed by Heike Kamerlingh Onnes in 1911. In everyday electrical conductors, such as copper or aluminum, resistance arises from the scattering of electrons as they move through the lattice of atoms, causing energy to dissipate as heat. However, in a superconductor, electrons pair up into what are called Cooper pairs, moving in a coordinated fashion that allows them to flow through the material without any scattering or energy loss. This zero resistance state means that an electrical current can, in theory, flow indefinitely without any input of energy, a concept that challenges our conventional understanding of electricity and energy conservation. The implications of this remarkable state of matter extend far beyond the laboratory, offering the potential for revolutionary improvements in the efficiency of electrical systems. The practical benefits of zero electrical resistance are profound. In power transmission, for instance, superconductors could drastically reduce the energy losses that currently occur when electricity travels over long distances through conventional wires. Today, a significant portion of generated electrical energy is wasted as heat due to resistance, which not only reduces efficiency, but also requires additional infrastructure to manage thermal effects. Superconducting cables, in contrast, would allow electricity to flow with perfect efficiency, potentially transforming national power grids and enabling the more effective distribution of renewable energy sources. Beyond transmission, superconductors are also vital components in devices like MRI machines and particle accelerators, where their ability to carry large currents without loss allows for strong and stable magnetic fields. These applications demonstrate how zero resistance not only conserves energy, but also enables technologies that would otherwise be impractical or impossible. Yet the journey from theoretical discovery to widespread application is not without challenges. The requirement for extremely low temperatures to achieve superconductivity has historically limited its use, as maintaining such conditions demands costly and complex cooling systems. Researchers are actively exploring high-temperature superconductors, materials that exhibit zero resistance at comparatively higher temperatures, sometimes achievable with liquid nitrogen cooling. These developments bring superconducting technologies closer to everyday use, reducing operational costs and expanding potential applications. In the realm of transportation, for example, superconducting magnets are central to maglev trains that float above tracks, eliminating friction and enabling smooth, rapid transit. Similarly, energy storage systems utilizing superconductors can quickly release stored electricity to stabilize power grids during demand fluctuations. Each practical implementation illustrates how zero electrical resistance can unlock new efficiencies and capabilities, provided that material science continues to advance in tandem with engineering solutions. Zero resistance property also opens doors to innovative computing technologies. Quantum computers, which promise to solve problems far beyond the reach of classical machines, rely heavily on superconducting circuits. In these systems, superconductivity enables the creation of qubits that maintain quantum coherence for longer periods, a critical factor in performing complex calculations accurately. The absence of resistance reduces thermal noise and energy dissipation, improving the stability and scalability of quantum processors. This interplay between zero resistance and quantum mechanics exemplifies the deep connection between fundamental physics and cutting-edge technology. As researchers continue to unravel the mysteries of superconducting materials, the potential for breakthroughs in information processing and data handling grows ever more tangible. As we consider the vast implications of zero electrical resistance, it becomes clear that superconductors represent more than just a scientific curiosity. They embody a frontier of technology with the power to reshape how we generate, transmit, store, and utilize energy. From the invisible currents flowing effortlessly through superconducting wires to the levitating trains gliding with magnetic grace. The promise of superconductivity inspires a vision of a more efficient and sustainable future. The ongoing quest to harness and expand this extraordinary phenomenon continues to drive innovation, guiding us toward new horizons where energy loss is a relic of the past. One of the most fascinating phenomena that distinguishes superconductors from ordinary conductors is known as the Meissner effect. When a material transitions into its superconducting state below a critical temperature, it exhibits a remarkable property. It expels magnetic fields from its interior. This expulsion means that the superconductor will actively drive out any magnetic flux lines that attempt to penetrate it, creating a perfect diamagnetic response. Unlike a simple perfect conductor, which would merely trap magnetic fields present at the time it became superconducting, the Meissner effect ensures that magnetic fields are completely excluded, revealing a distinct and fundamental change in the material's electromagnetic behavior. This unique magnetic property is not only a signature of superconductivity, but also a critical factor in many of the practical applications that rely on superconductors. The implications of the Meissner effect extend far beyond its theoretical elegance. By expelling magnetic fields, superconductors can cause magnetic levitation, a phenomenon where a magnet can seemingly float above a superconducting surface without any mechanical support. This levitation occurs because the superconductor generates currents on its surface that produce magnetic fields opposing the external magnet, stabilizing it in mid-air. Such magnetic levitation has profound technological potential, especially in the development of frictionless transportation systems, such as maglev trains. These trains glide above tracks with negligible resistance, promising faster, quieter, and more energy-efficient travel compared to conventional wheels on rails. The Meissner effect thus transforms abstract physics into tangible innovations that could reshape urban mobility and infrastructure. Beyond transportation, the expulsion of magnetic fields in superconductors plays a pivotal role in the field of medical imaging and scientific instrumentation. Magnetic resonance imaging, or MRI machines, rely on powerful superconducting magnets to generate stable and intense magnetic fields with minimal energy loss. The Meissner effect ensures that these superconducting coils maintain their magnetic integrity, allowing for precise imaging of the human body without the need for continuous electrical input. Similarly, particle accelerators and other research facilities utilize superconducting magnets to steer and focus particle beams, all made possible by the unique magnetic properties born from this effect. These applications emphasize how the fundamental behavior of superconductors translates into tools that enhance our understanding of the universe and improve human health. The theoretical underpinnings of the Meissner effect have also guided scientists in exploring new classes of materials and developing novel superconducting technologies. Researchers examine how different superconductors respond to varying magnetic fields, temperatures, and pressures to optimize their performance for specific uses. This knowledge is critical in the creation of superconducting quantum interference devices, or SQUIDs, which exploit the magnetic sensitivity of superconductors for highly precise measurements of magnetic flux. Such devices have applications ranging from geological surveys to brain activity monitoring, illustrating the broad reach of superconductors' magnetic properties. The ongoing study of the Meissner effect thus not only deepens our fundamental understanding, but also continuously expands the horizon of practical applications. As we reflect on the role of the Meissner effect in revealing the unique magnetic nature of superconductors, it becomes clear that this phenomenon is central to their transformative potential. By fundamentally altering how materials interact with magnetic fields, superconductors open pathways to technologies once thought to be the domain of science fiction. From levitating trains to advanced medical devices, the expulsion of magnetic fields is a critical enabler of innovation. The journey to harness this effect fully is ongoing, inviting us to imagine a future where the seamless integration of superconducting materials could redefine energy, transportation, and instrumentation. This exploration leads us naturally to consider the broader implications of superconductivity in energy storage and transmission, where the absence of resistance and magnetic stability converge to create remarkable possibilities. Superconductors, remarkable in their ability to conduct electricity without resistance, are broadly classified into two categories, Type 1 and Type 2. This distinction arises from their differing responses to magnetic fields and their unique internal structures. Type 1 superconductors, often elemental metals like lead or mercury, exhibit a complete expulsion of magnetic fields below a critical temperature and critical magnetic field. This behavior, known as the Meissner effect, is sharp and absolute in Type 1 materials, which revert abruptly to their normal, resistive state once the magnetic field surpasses a critical threshold. Their simplicity provides a clear window into the fundamental nature of superconductivity, yet their practical use is limited due to low critical magnetic fields and temperatures. Understanding Type 1 superconductors lays the groundwork for appreciating the more complex, yet technologically promising behaviors found in Type 2 superconductors. Type 2 superconductors introduce a fascinating complexity that opens doors to many practical applications. Unlike their Type 1 counterparts, Type 2 materials, often alloys or ceramic compounds, allow magnetic fields to penetrate through in quantized vortices while still maintaining superconductivity. This mixed state, persisting between two critical magnetic field values, permits them to function under much higher magnetic fields and temperatures. The ability of Type 2 superconductors to sustain superconductivity amidst strong magnetic environments makes them particularly valuable for high field applications. These materials are foundational in technologies such as magnetic resonance imaging, particle accelerators, and maglev trains, where powerful and stable magnetic fields are essential. The nuanced interplay between magnetic flux lines and the superconducting state in Type 2 materials exemplifies the richness of superconducting physics and its potential to transform industry and research. Differentiating between Type 1 and Type 2 superconductors is not simply a matter of classification, but a key to unlocking their varying behaviors and practical usability. Type 1 superconductors, with their complete magnetic field expulsion, are ideal for exploring pure superconducting phenomena in controlled environments. Meanwhile, the robustness of Type 2 superconductors under strong magnetic fields and higher temperatures enables their incorporation into real-world devices and infrastructure. This understanding guides material scientists and engineers as they tailor superconducting materials to specific needs, balancing factors like critical temperature, magnetic field tolerance, and mechanical properties. By exploring and manipulating these characteristics, we edge closer to realizing superconductors' full promise in energy transmission, medical technology, and transportation. The subtle distinctions between these types illuminate the path forward in both fundamental science and innovative applications. As we appreciate the nuanced differences between Type 1 and Type 2 superconductors, it becomes increasingly evident how these materials shape the landscape of future technologies. Their distinctive behaviors under magnetic influence dictate not only the environments in which they can operate, but also the scope of their integration into complex systems. The exploration of these superconducting types invites ongoing research, pushing the boundaries of what materials can achieve. This journey toward optimizing superconductors for various uses highlights the dynamic interplay between theoretical understanding and practical engineering. With each advancement, the horizon expands, revealing new possibilities in energy-efficient power grids, ultra-sensitive sensors, and advanced medical diagnostics. Our next focus will naturally turn to how these superconductors are harnessed in energy storage and transmission, where their unique properties promise revolutionary improvements. The discovery of high-temperature superconductors marked a significant milestone in the field of materials science, offering a new realm of possibilities that extend beyond the constraints of traditional low-temperature superconductors. Unlike their predecessors, which require cooling to near absolute zero using liquid helium, high-temperature superconductors operate at temperatures achievable with liquid nitrogen, a more practical and cost-effective coolant. This advancement not only alleviates some of the logistical challenges associated with maintaining ultra-cold environments, but also brings the dream of widespread superconducting technologies closer to reality. These materials, often complex copper oxide ceramics known as cuprates, exhibit superconductivity at temperatures well above the boiling point of liquid nitrogen, around 77 Kelvin. This relatively accessible temperature threshold reduces operational costs and opens up new avenues for integrating superconductors into everyday applications. The theoretical potential of high-temperature superconductors is vast and compelling. Their ability to conduct electricity without resistance means that power loss in transmission lines could be drastically reduced, resulting in more efficient energy distribution networks. In addition, Their unique magnetic properties allow for the creation of powerful electromagnets that require less energy to maintain, which could transform technologies ranging from maglev trains to particle accelerators. On the quantum scale, these materials may also play a vital role in the development of quantum computing, providing stable platforms for qubits that operate with minimal energy dissipation. The interplay between superconductivity and magnetism in these materials is still an active area of research, promising to unlock deeper understanding of their fundamental physics. This ongoing inquiry not only enriches theoretical frameworks, but also informs the engineering of next-generation devices that harness these remarkable phenomena. Practical applications of high-temperature superconductors are steadily emerging as research transitions from laboratory experiments to real-world implementation. In power grids, superconducting cables can carry immense currents with negligible losses, offering a solution to the growing demand for sustainable and efficient energy management. Hospitals benefit from high-temperature superconducting magnets used in magnetic resonance imaging, which are more compact and energy efficient than conventional magnets. Additionally, these superconductors enable the development of sensitive magnetic sensors capable of detecting minute changes in magnetic fields, useful in geological surveys and security screening. The adaptability of these materials under varied operational conditions further enhances their appeal, making them suitable for incorporation into devices that require stable, high-performance conductors. As fabrication techniques improve and costs decrease, the integration of high-temperature superconductors into commercial technologies becomes increasingly viable. Despite their promise, challenges remain in the widespread adoption of high-temperature superconductors. These materials often exhibit brittleness and require precise fabrication methods to maintain their superconducting properties, complicating their integration into flexible or large-scale infrastructure. Moreover, understanding the mechanisms behind their relatively high critical temperatures continues to be a focus of condensed matter physics, as unlocking these secrets may lead to the development of even more robust and higher temperature superconductors. Advances in materials science and engineering aim to overcome these hurdles by developing new compounds and composites that combine superconducting performance with mechanical durability. The collaborative efforts between theoretical physicists, chemists, and engineers drive the evolution of these materials, from experimental curiosities to practical tools that could reshape multiple technological sectors. As high-temperature superconductors edge closer to widespread utility, their role in energy storage and transmission becomes increasingly significant. The prospect of lossless power lines and powerful superconducting magnets invites a re-evaluation of how energy systems can be designed for maximum efficiency and sustainability. Future research will likely focus on optimizing these materials for integration into smart grids, renewable energy infrastructures, and high-capacity energy storage devices. The journey toward harnessing the full potential of superconductivity continues to inspire innovation, promising to transform the ways in which we generate, distribute, and utilize energy. With this foundation laid, we now turn our attention to the specific advancements in energy storage and transmission technologies, where superconductors offer transformative possibilities. To truly appreciate the remarkable phenomenon of superconductivity, one must delve into the fundamental principles that govern it. At the heart of this understanding lies the Bardeen-Cooper-Schrieffer theory, commonly known as the BCS theory. Developed in the late 1950s, this groundbreaking framework revolutionized the way physicists perceive electron behavior within certain materials cooled to near absolute zero. According to the theory, superconductivity emerges when electrons, which normally repel each other due to their like charges, instead form paired states known as Cooper pairs. These pairs move through a crystal lattice with remarkable coordination, avoiding the typical scattering and resistance that disrupt normal electrical conduction. This elegant pairing mechanism allows electrical current to flow without any loss, a defining characteristic of superconductors. The BCS theory not only provides a microscopic explanation for zero resistance, but also accounts for the energy gap observed in superconducting materials, offering a comprehensive model that has withstood decades of experimental verification. The implications of the BCS theory extend beyond the realm of pure physics, as it lays the groundwork for numerous practical applications that harness the power of superconductivity. By understanding the conditions under which Cooper pairs form and persist, scientists and engineers can design materials and devices that exploit these properties for real-world benefit. For example, superconducting magnets, which generate intense magnetic fields without energy loss, rely on materials that exhibit robust Cooper pairing. These magnets are integral to magnetic resonance imaging, or MRI machines, enabling detailed and non-invasive glimpses into the human body. Furthermore, the phenomenon explained by BCS theory informs the development of superconducting quantum interference devices, or SQUIDs, which are used in sensitive magnetic field detection and have applications in medicine, geology, and fundamental research. The precise control over electron pairing also opens the door to advances in quantum computing, where superconducting circuits serve as qubits, the basic units of quantum information. Beyond medical imaging and quantum technologies, BCS theory also inspires innovative approaches to energy efficiency and transmission. High-temperature superconductors, although not fully explained by the classical BCS framework, build upon its foundational concepts and push the boundaries of what is technologically achievable. The ability to transmit electricity without resistance can dramatically reduce energy losses that currently occur in conventional power grids, which dissipate a significant portion of generated electricity as heat. Superconducting cables, cooled below their critical temperature, can carry vast amounts of current over long distances, enhancing grid capacity and stability. This transformation is especially relevant as the world increasingly relies on renewable energy sources, which demand flexible and efficient transmission networks. By combining the insights of BCS theory with ongoing material science advancements, researchers strive to create superconductors that operate at higher temperatures and in more practical conditions, ultimately making these technologies more accessible and cost-effective. The theoretical foundation provided by the BCS theory also informs the exploration of novel superconducting materials and their potential applications. In particle accelerators, for instance, superconducting radio frequency cavities utilize the zero-resistance state to sustain powerful electromagnetic fields essential for particle acceleration. These advancements have propelled research in fundamental physics, enabling experiments that probe the most minute aspects of matter and energy. Similarly, in transportation, superconducting magnetic levitation, or maglev trains, leverage superconducting magnets to achieve frictionless, high-speed travel. The precise understanding of electron pairing and lattice interactions from BCS theory guides the refinement of these complex systems, ensuring stability and efficiency. As the field evolves, the interplay between theory and application continues to deepen, fostering new innovations in diverse sectors ranging from telecommunications to medical diagnostics. The BCS theory remains a cornerstone of this ongoing journey, illuminating the path toward future breakthroughs. Despite the remarkable progress achieved in understanding and applying superconductors, significant challenges remain that hinder their widespread use. One of the primary obstacles lies in the demanding conditions required to sustain superconductivity. Most known superconducting materials operate at extremely low temperatures, often close to absolute zero, necessitating sophisticated and costly cooling systems. These cryogenic environments, while effective in laboratory settings and specialized applications, present practical difficulties when considering large-scale or everyday use. The energy and infrastructure required to maintain such conditions limit the accessibility of superconducting technology, confining its benefits to niche areas. Furthermore, the fragility of many superconducting materials under mechanical stress or magnetic fields complicates their integration into robust devices. These inherent limitations underscore the importance of ongoing research aimed at discovering new materials that exhibit superconductivity at higher temperatures or under more manageable conditions. Another challenge in superconductor research involves the complexity of material composition and fabrication. High-temperature superconductors, such as certain copper oxides, exhibit superconductivity at temperatures significantly above those of conventional superconductors, but still require cooling with liquid nitrogen or similar methods. However, the crystal structures of these materials are often intricate and sensitive to imperfections. Slight deviations in their chemical makeup or crystalline arrangement can drastically reduce their superconducting properties or introduce instability. Producing these materials consistently and at scale remains a formidable task. Moreover, integrating them into electronic circuits or devices calls for innovative engineering solutions to preserve their delicate properties while enabling practical functionality. Researchers continually experiment with doping techniques, pressure adjustments, and novel synthesis methods to fine-tune these compounds. The goal is to develop superconductors that not only operate under less extreme conditions, but also maintain their performance in everyday applications. Beyond material challenges, there are also theoretical puzzles that continue to intrigue scientists. While the BCS theory elegantly explains conventional superconductivity, it falls short in fully describing high-temperature superconductors and other unconventional types. These materials exhibit behaviors that hint at more complex interactions within their electronic structures, suggesting that our understanding of superconductivity is still evolving. Unlocking these mysteries is crucial, as it may lead to the design of new materials with superior and more practical properties. Experimental techniques such as advanced spectroscopy and quantum simulations are increasingly employed to probe these phenomena at microscopic levels. The insights gained contribute to the broader field of condensed matter physics and may pave the way for breakthroughs not only in superconductivity, but also in related quantum technologies. This continuous interplay between theory and experiment drives the field forward, despite the many unresolved questions. Practical applications of superconductors also encounter engineering hurdles. For instance, in power transmission, superconducting cables offer the promise of near zero energy loss, which could revolutionize electrical grids. However, the deployment of such cables requires not only materials that retain superconductivity at feasible temperatures, but also designs that withstand environmental factors and mechanical stress over long periods. Cooling systems must be reliable and economically viable, and integration with existing infrastructure demands careful planning and innovation. The manufacturing costs and maintenance complexity currently outweigh the benefits for many utilities, slowing adoption despite the clear advantages. Similarly, in medical imaging, superconducting magnets are vital for MRI machines, yet the need for continuous cooling and material stability remains a consideration. Progress in cryogen-free systems and more resilient superconductors is gradually addressing these issues, but a fully optimized solution is still on the horizon. Understanding these current challenges highlights why the practical and widespread use of superconductors remains difficult, despite their extraordinary potential. The pursuit of materials that exhibit superconductivity at or near room temperature continues to be a driving force in research, promising to unlock transformative applications across energy, transportation, medicine, and beyond. Each incremental discovery builds upon the foundational theories and experimental techniques developed over decades, weaving a complex tapestry of knowledge and innovation. As the scientific community delves deeper into the subtleties of electron behavior and material science, the hope is to transcend the limitations that have thus far constrained superconducting technologies. This ongoing journey, filled with both challenges and opportunities, sets the stage for future advancements that may one day bring these remarkable phenomena into everyday life. One of the most promising avenues for the application of superconductors lies in the realm of power grids. Traditional electrical transmission systems rely on conductive materials like copper and aluminum, which inherently possess electrical resistance. This resistance causes energy to dissipate as heat during transmission, leading to significant energy losses over long distances. In contrast, superconductors exhibit zero electrical resistance when cooled below a critical temperature, allowing electric current to flow without any energy loss. This extraordinary property opens the door to reimagining how electricity can be transmitted more efficiently across vast networks. By replacing conventional cables with superconducting materials, it becomes possible to drastically reduce the energy lost in transit, thereby enhancing the overall efficiency of power delivery systems. The theoretical benefits of integrating superconductors into power grids extend beyond mere energy savings. Superconducting cables can carry much higher current densities than traditional conductors, enabling the transmission of larger amounts of power through smaller, lighter cables. This capability can alleviate the physical constraints and environmental impact of expanding power infrastructure, especially in urban settings where space is limited. Furthermore, superconducting technology can contribute to increased grid stability and reliability. Because superconductors can respond rapidly to changes in current and voltage, they offer the potential to enhance the control and management of power flows, reducing the risk of outages and improving the resilience of electrical networks to fluctuations or faults. These attributes underscore the transformative potential of superconductors in shaping the future of energy infrastructure. Practical applications of superconductors in power transmission have already begun to emerge in pilot projects and specialized installations around the world. High-temperature superconducting cables, cooled by liquid nitrogen, have demonstrated their ability to integrate seamlessly with existing grid components while providing superior performance. These installations serve as valuable testbeds for understanding the complexities of scaling superconducting technologies for widespread use. Despite the challenges of maintaining the low temperatures required for superconductivity, advances in cryogenic engineering and material science continue to improve the feasibility and cost-effectiveness of these systems. As these technologies mature, they hold the promise of revolutionizing how electricity is managed and distributed, contributing to a more sustainable and efficient energy future. Beyond transmission lines, superconductors also find potential roles in power grid components, such as transformers, fault current limiters, and energy storage devices. Superconducting transformers, for example, can operate with higher efficiency and reduced size compared to conventional transformers, reducing energy losses during voltage conversion. Fault current limiters made from superconducting materials can quickly respond to overloads, protecting the grid from damage and minimizing downtime. Additionally, superconducting magnetic energy storage systems can store and release large amounts of energy rapidly, helping to balance supply and demand fluctuations in renewable energy sources like wind and solar. Each of these applications reflects a broader vision where superconducting technologies contribute to a more resilient, flexible, and eco-friendly power infrastructure. One of the most captivating applications of superconductors lies in the realm of magnetic levitation, particularly in transportation systems known as maglev trains. These trains utilize superconducting magnets to create powerful magnetic fields that can lift and propel vehicles without physical contact with the tracks. This levitation eliminates friction, one of the primary forces limiting speed and efficiency in conventional rail systems. The superconducting magnets, cooled to extremely low temperatures, maintain their zero resistance state, enabling persistent currents that generate stable and strong magnetic fields. This technology allows maglev trains to glide smoothly above the guideway, reducing mechanical wear and noise, while offering a quieter and more comfortable ride. The practical implications of superconducting maglev technology extend beyond mere speed. Because these trains face minimal friction, they require less energy to maintain high velocities, making them more energy efficient compared to traditional wheeled trains. Additionally, the lack of direct contact with the track reduces maintenance requirements, as there is no physical degradation of rails or wheels due to friction. This leads to longer operational lifespans and lower overall costs. Furthermore, the precise control enabled by superconducting magnets allows for smoother acceleration and deceleration, enhancing passenger safety and comfort. The potential to reach speeds exceeding 600 kilometers per hour opens doors to revolutionary changes in regional and intercity travel, shrinking distances and connecting communities more effectively. Beyond high-speed passenger travel, superconducting magnetic levitation has promising applications in urban transit and freight transport. In densely populated cities, maglev systems could offer quiet, efficient alternatives to traditional subways and buses, reducing traffic congestion and pollution. For freight, magnetic levitation could enable the rapid movement of goods with minimal energy consumption and reduced mechanical wear on transport infrastructure. Researchers continue to explore ways to improve the materials and cooling methods required for superconductors to operate more economically and reliably. Advances in high-temperature superconductors may eventually allow maglev technology to become more accessible and widespread, integrating seamlessly into existing transportation networks and reshaping how people and goods move through our world. The theoretical uses of superconductors in transportation inspire visions of a future where travel is not only faster and quieter, but also more sustainable. By reducing reliance on fossil fuels through energy-efficient magnetic levitation, maglev trains can contribute to lowering greenhouse gas emissions associated with conventional transportation. The integration of superconducting technology with renewable energy sources further enhances this environmental benefit. As research progresses, the challenges of cost, infrastructure development, and widespread adoption remain. Yet the promise of frictionless, rapid transit remains a compelling incentive. This harmony of advanced physics and engineering exemplifies the transformative potential of superconductors beyond the realm of power grids. Continued innovation in superconducting materials and magnet design steadily brings these futuristic transportation concepts closer to reality. The exploration of magnetic levitation naturally leads us toward other dynamic uses of superconducting magnets in industries such as medical imaging and particle acceleration, where precise and powerful magnetic fields are equally essential. As we consider these diverse applications, the role of superconductors expands, weaving through various facets of modern technology and infrastructure. of the most profound impacts of superconductors lies in the realm of medical imaging, where they have revolutionized the capabilities of magnetic resonance imaging, or MRI technology. Superconducting magnets, which can generate stable and extremely strong magnetic fields with minimal energy loss, are at the heart of these machines. Unlike conventional magnets, superconductors carry electric currents without resistance when cooled to cryogenic temperatures, allowing MRI machines to produce magnetic fields that are both intense and uniform. This uniformity is critical for acquiring detailed images of the body's internal structures, enabling clinicians to detect abnormalities with exceptional clarity and precision. The ability to visualize soft tissues non-invasively has transformed diagnostic medicine, empowering doctors to identify conditions such as tumors, neurological disorders, and cardiovascular diseases much earlier than was previously possible. The use of superconductors in MRI technology also contributes to the machine's energy efficiency and operational stability. Since superconducting coils eliminate electrical resistance, they require far less power once the initial cooling is achieved, making the systems more sustainable over time, despite their complex cooling systems involving liquid helium. This efficiency not only reduces costs, but also enhances the reliability of MRI machines, ensuring consistent performance during extended scanning sessions. Additionally, the strong magnetic fields generated by superconducting magnets facilitate advanced imaging techniques such as functional MRI, fMRI, which maps brain activity by detecting changes in blood flow. Such capabilities have opened new frontiers in neuroscience and psychology, providing insights into the workings of the human brain without invasive procedures. The integration of superconductors thus continues to refine imaging resolution and speed, broadening the scope of diagnostic possibilities. Beyond medical imaging, the principles behind superconducting magnets inspire a range of potential future applications in healthcare and research. For instance, the development of portable or more compact MRI systems utilizing high-temperature superconductors could make advanced imaging accessible in remote or underserved regions, transforming global health outcomes. Moreover, the precise control of magnetic fields afforded by superconductors is instrumental in particle accelerators used for cancer treatment, such as proton therapy. Superconducting magnets focus particle beams with remarkable accuracy, minimizing damage to healthy tissues while targeting malignant cells. As research advances, new superconducting materials with higher critical temperatures and improved mechanical properties promise to further enhance these technologies, potentially leading to more affordable, efficient, and versatile medical devices. The ongoing synergy between superconducting science and medicine exemplifies how foundational physics can unlock transformative healthcare solutions. The deployment of superconductors in MRI technology not only exemplifies the practical benefits of these extraordinary materials, but also highlights the delicate balance between physics and engineering required to bring such innovations to life. The challenges of maintaining ultra-low temperatures, ensuring stability of magnetic fields, and integrating superconductors into complex systems reflect a continuous interplay of scientific understanding and technological ingenuity. Yet, each advancement in superconducting technology brings us closer to more refined diagnostic tools capable of revealing the intricate details of human anatomy and physiology without discomfort or risk. As we continue to push the boundaries of what superconductors can achieve, their influence extends beyond medicine into realms such as quantum computing and energy transmission, where their unique properties hold equally transformative promise. In considering the impact of superconductors on medical imaging, one naturally turns to their role in other scientific arenas that demand precision and power. Particle accelerators, for example, rely on superconducting magnets to steer and accelerate charged particles to near light speeds, enabling discoveries about the fundamental nature of matter and energy. These instruments, much like MRI machines, benefit profoundly from the lossless current flow and intense magnetic fields that superconductors provide. The journey from magnetic levitation and medical diagnostics to high-energy physics underscores the versatile and essential nature of superconducting technology in modern science and industry. As we explore these interconnected applications, the horizon of superconducting innovation continues to expand, inviting us to imagine the possibilities yet to unfold. Superconductors have emerged as a cornerstone in the rapidly evolving field of quantum computing, a domain that seeks to harness the peculiar principles of quantum mechanics to perform computations far beyond the reach of classical machines. At the heart of many quantum computers lie superconducting qubits, tiny circuits cooled to temperatures near absolute zero, where electrical resistance vanishes entirely. This unique property allows these qubits to oscillate between quantum states with remarkable coherence and minimal energy loss. Unlike classical bits that can only exist as 0 or 1, superconducting qubits exploit the phenomenon of superposition, enabling them to represent multiple states simultaneously. This intrinsic parallelism opens the door to solving complex problems in cryptography, material science, and optimization that would otherwise require infeasible amounts of time on traditional computers. The theoretical potential of superconducting qubits extends beyond mere computational speed. They also offer a promising path toward fault-tolerant quantum computing, where errors caused by environmental noise and imperfections are actively detected and corrected. This capability is essential because quantum information is incredibly delicate, easily disrupted by the smallest external disturbances. Superconducting circuits are particularly well suited for integrating quantum error correction protocols thanks to their scalability and compatibility with existing semiconductor fabrication techniques. Researchers are continually refining the design and materials of these qubits to enhance their coherence times and operational fidelity. This progress suggests a future where quantum processors, composed of thousands or even millions of superconducting qubits, could perform intricate simulations of molecular interactions or optimize complex logistical networks in ways that classical computers simply cannot match. Beyond their theoretical promise, superconducting qubits have already found practical applications in experimental quantum processors developed by leading technology companies and research institutions worldwide. These quantum machines, though still in the early stages, are being deployed to explore problems in chemistry, cryptography, and machine learning. For instance, superconducting quantum processors have been used to simulate the behavior of small molecules, potentially accelerating the discovery of new pharmaceuticals and advanced materials. Moreover, their ability to factor large numbers efficiently could eventually revolutionize cybersecurity by challenging current encryption methods. The rapid advancements in cryogenic technology and microwave control systems further bolster the feasibility of operating superconducting qubits at scale. As a result, superconducting quantum computing stands at the forefront of a new technological revolution, poised to unlock computational capabilities previously thought impossible. While the journey toward fully functional, large-scale quantum computers remains complex and filled with challenges, the role of superconductors in this endeavor is undeniably pivotal. Their unique properties enable the delicate manipulation of quantum states with precision and stability, bridging the gap between theoretical quantum mechanics and practical technology. As research continues to deepen our understanding of superconducting materials and quantum coherence, innovations may arise that further enhance qubit performance and integration. This ongoing exploration not only enriches our grasp of fundamental physics, but also inspires new applications that could transform fields ranging from artificial intelligence to financial modeling. The interplay between superconductivity and quantum information science exemplifies the profound ways in which advanced materials influence the trajectory of human knowledge and capability. One of the most promising applications of superconductors lies within the realm of energy storage, particularly through a technology known as superconducting magnetic energy storage, or SMES. This method harnesses the remarkable ability of superconductors to conduct electricity without resistance, enabling the storage of energy in the magnetic field generated by a persistent current flowing through a superconducting coil. Unlike conventional batteries or capacitors, SMES systems can deliver and absorb energy almost instantaneously, making them exceptionally efficient for stabilizing power grids and managing fluctuations in energy supply. Their rapid response time is especially crucial in an era where renewable energy sources, such as solar and wind, introduce variability into the electrical grid. By buffering these fluctuations, SMES can help maintain a steady flow of electricity, ensuring the reliability and robustness of power systems. The theoretical underpinnings of SMES are deeply rooted in the physics of superconductivity and magnetic fields. When a superconducting coil is energized, it generates a magnetic field that can store large amounts of energy with minimal losses. Because the current in the coil encounters no electrical resistance, the energy can be retained indefinitely, limited primarily by the quality of the superconducting material and the cooling systems that maintain it below critical temperatures. These factors present both opportunities and challenges, as the efficiency of SMES depends on advances in material science, cryogenics, and system design. Researchers continue to explore novel superconducting materials that operate at higher temperatures, which would reduce the complexity and cost associated with cooling. As these materials evolve, so too does the potential for SMES to become a more practical and widespread solution for energy storage in various sectors. In practical terms, SMES systems have found their place in specialized applications where rapid energy discharge and high efficiency are paramount. For instance, they are used to stabilize electrical grids by smoothing out sudden surges or drops in power demand, preventing blackouts and improving overall grid resilience. Additionally, SMES can provide short bursts of power to critical infrastructure, such as hospitals or data centers, where uninterrupted energy supply is essential. Beyond grid stabilization, the technology holds promise in supporting the integration of renewable energy sources by compensating for their intermittent nature. As renewable penetration increases, the ability to quickly store and release energy becomes vital to balancing supply and demand, reducing reliance on fossil fuel backup systems. These practical implementations not only highlight the versatility of superconductors, but also emphasize their role in enabling a cleaner and more sustainable energy future. Looking ahead, the continued development of SMES technology may lead to even more innovative uses that extend beyond traditional power systems. For example, the unique characteristics of superconductors could be harnessed in transportation, such as magnetic levitation trains, where energy storage and rapid discharge capabilities enhance efficiency and performance. Furthermore, SMES could play a role in emerging energy networks that require decentralized and flexible storage solutions, adapting to the dynamic demands of smart grids and urban energy ecosystems. As the scientific community deepens its understanding of superconducting phenomena and refines engineering approaches, these systems are poised to become integral components of modern energy infrastructure. The synergy between superconducting materials and energy storage exemplifies how fundamental physics can translate into transformative technologies that shape the way we generate, store, and use energy. Superconductors are materials that exhibit a remarkable phenomenon. They conduct electricity with zero resistance when cooled below a certain critical temperature. This unique property allows electrical currents to flow indefinitely without energy loss, a feature that has fascinated scientists and engineers for decades. Traditionally, achieving superconductivity required extremely low temperatures, often near absolute zero, which limited practical applications due to the complexity and expense of cooling systems. However, recent breakthroughs in materials science have brought the possibility of room temperature superconductivity closer to reality. These advances involve novel compounds and innovative methods of manipulating atomic structures, enabling superconducting behavior under conditions far less demanding than before. The implications of such discoveries are profound, as they could dramatically reduce the cost and complexity of superconducting technologies, paving the way for widespread adoption across various industries. The theoretical uses of room temperature superconductors span a broad spectrum of fields, each promising revolutionary improvements in efficiency and performance. In the realm of energy, superconducting cables could transmit electricity over vast distances without loss, addressing significant challenges in power distribution. This would enhance grid reliability and facilitate the integration of renewable energy sources by minimizing wasted energy. In transportation, Superconductors could enable more efficient magnetic levitation trains, reducing friction and allowing for quieter, faster travel. Medical technologies also stand to benefit. For instance, superconducting magnets play a crucial role in magnetic resonance imaging, and room temperature variants could make such devices more accessible and affordable. Furthermore, quantum computing, which relies on superconducting circuits to maintain qubits, could advance significantly with materials that operate without the need for extreme cooling. Such theoretical applications underscore the transformative potential of room temperature superconductors in reshaping how we approach technology and infrastructure. Practical applications of superconductors have already begun to manifest in specialized environments, but room temperature superconductivity promises to expand their presence into everyday technologies. Power utilities could deploy superconducting fault current limiters to protect electrical networks from surges without energy loss. Similarly, superconducting magnetic energy storage systems may become more viable, offering rapid response and high-efficiency storage solutions that complement intermittent renewable sources like wind and solar. In transportation, the prospect of levitating trains operating without the need for cryogenic cooling could revolutionize public transit, making it faster and more energy efficient. Industrial applications could include highly sensitive magnetometers for geophysical exploration and advanced particle accelerators for research. The economic impact of eliminating the cooling requirements could be substantial, reducing both initial investment and operational costs, thereby accelerating commercialization. These practical benefits, once confined to theoretical discussions, are now within reach, thanks to the ongoing refinement of superconducting materials. As research continues, the scientific community remains focused on understanding the underlying mechanisms that enable room temperature superconductivity, striving to optimize materials for stability, scalability, and integration into existing systems. Interdisciplinary collaboration among physicists, chemists, and engineers is essential to overcoming challenges such as material brittleness and maintaining superconducting properties under variable conditions. Innovations in fabrication techniques, including thin film deposition and nanostructuring, are contributing to these efforts by allowing precise control over material properties. Moreover, computational modeling and machine learning are increasingly employed to predict promising compounds and guide experimental synthesis. This evolving landscape of research reflects a broader trend in materials science, where the convergence of theory and experimentation accelerates discovery. As these endeavors progress, the prospect of embedding room temperature superconductors into the fabric of modern technology becomes ever more tangible. Looking beyond the laboratory, the integration of room temperature superconductors into real-world applications will depend on thoughtful engineering and economic considerations. Manufacturing processes must be developed to produce these materials at scale while preserving their unique electrical properties. Infrastructure adaptations will be necessary to accommodate new superconducting components within power grids, transportation networks, and medical devices, requiring coordinated efforts across industries and governments. Additionally, environmental impacts and resource availability of the constituent elements must be evaluated to ensure sustainable development. Despite these challenges, the promise of superconductors operating at ambient conditions inspires optimism for a future where energy loss is minimized, technologies are more efficient, and new possibilities emerge. This ongoing journey from fundamental physics to applied innovation exemplifies the dynamic nature of scientific progress and its potential to transform our world. One of the most compelling environmental benefits of superconductors arises from their remarkable ability to conduct electricity without resistance. In traditional conductors, electrical currents encounter resistance that causes energy to dissipate as heat, resulting in significant power losses across transmission lines and electronic devices. Superconductors, by contrast, allow current to flow freely without such losses, dramatically improving energy efficiency. When integrated into power grids, this property could reduce the amount of electricity wasted during transmission, leading to lower fuel consumption at power plants and decreased emissions of greenhouse gases. Furthermore, the enhanced efficiency of superconducting systems can support the integration of renewable energy sources such as wind and solar power by stabilizing voltage and reducing energy loss during distribution. This synergy between superconductors and renewable technologies presents a promising pathway towards a more sustainable and environmentally responsible energy landscape. Beyond the electrical grid, superconductors hold potential for transforming transportation in ways that could significantly reduce carbon footprints. Magnetic levitation trains, or maglevs, employ superconducting magnets to create frictionless travel, allowing trains to glide smoothly at high speeds with minimal energy consumption. By replacing conventional diesel or electric trains, superconducting maglev systems could reduce reliance on fossil fuels and lower air pollution in urban environments. Additionally, the use of superconducting motors in electric vehicles could increase power efficiency and reduce battery size requirements, extending driving range while decreasing the environmental impact associated with battery production and disposal. These advances in transportation technologies highlight the role of superconductors in enabling cleaner mobility, contributing to a reduction in global greenhouse gas emissions and enhancing the quality of urban air. In the realm of medical and scientific equipment, superconductors contribute to environmental sustainability through enhanced performance and reduced energy demands. Magnetic resonance imaging, MRI machines, which rely on superconducting magnets, deliver high-resolution images for diagnostic purposes with greater efficiency than conventional electromagnets. The lower energy consumption of superconducting magnets not only decreases operational costs, but also reduces the carbon footprint of healthcare facilities. Similarly, particle accelerators and research instruments that utilize superconducting technology benefit from improved energy efficiency, enabling scientific exploration with less environmental strain. Moreover, the development of compact and efficient superconducting devices may facilitate decentralized healthcare and research infrastructures, potentially reducing the need for large, energy-intensive central facilities. This aspect of superconducting technology underscores the interconnectedness of scientific innovation and environmental stewardship. While the environmental advantages of superconductors are promising, it is essential to consider the sustainable sourcing and life cycle of the materials involved. Many superconductors contain rare or precious elements whose extraction and processing can have significant ecological footprints. Responsible mining practices, recycling strategies, and the search for abundant, non-toxic alternatives are vital to ensuring that the adoption of superconducting technologies does not introduce new environmental challenges. Additionally, the production and disposal phases of superconducting devices must be managed carefully to minimize waste and pollution. As research progresses, the design of superconductors with environmentally benign compositions and scalable manufacturing methods will be crucial to realizing their full potential as green technologies. This holistic approach to materials science and engineering reflects a broader commitment to sustainability in technological advancement. Ultimately, the integration of superconductors into everyday technologies invites a future where energy use is more efficient and environmental impacts are thoughtfully minimized. Their unique properties enable innovations that align with global efforts to combat climate change and promote healthier ecosystems. As scientists and engineers continue to refine these materials and their applications, the pathways toward greener energy systems, cleaner transportation, and sustainable industry become clearer. This ongoing evolution in technology embodies a harmonious blend of scientific discovery and ecological consciousness, setting the stage for the transformative possibilities that superconductors may unlock in the years ahead. In the quest for sustainable and abundant energy, fusion reactors represent a pinnacle of scientific ambition. These reactors seek to replicate the process that powers our sun, fusing atomic nuclei to release vast amounts of energy without the harmful byproducts associated with fossil fuels. Central to this process is the need to contain and control plasma, an extremely hot, charged state of matter within magnetic fields strong enough to prevent it from touching reactor walls and losing energy. Here, superconductors emerge as vital components. Their ability to conduct electricity with zero resistance allows the generation of powerful magnetic fields without the energy losses typical of conventional conductors. This unique property makes superconducting magnets indispensable in the magnetic confinement of plasma, ensuring the stability and efficiency necessary for sustained fusion reactions. The theoretical uses of superconductors in fusion technology extend beyond just magnetic confinement. Superconducting coils can be designed to produce stable, high-intensity magnetic fields that are crucial for shaping and controlling plasma behavior. This precise control helps in maintaining the right temperature and pressure conditions required for fusion to occur. Additionally, The durability and efficiency of superconducting materials reduce the operational costs of fusion reactors, moving the technology closer to commercial viability. The promise of fusion energy lies in its potential to provide a nearly limitless supply of clean power with minimal environmental impact. Superconductors, by enabling the control systems necessary for these reactions, become key enablers in realizing this vision of energy abundance. Beyond fusion reactors, superconductors have practical applications in many other fields where efficient energy transmission and strong magnetic fields are needed. In medical imaging, for instance, superconducting magnets form the core of MRI machines, allowing for detailed internal scans without invasive procedures. In transportation, superconducting materials are being explored for maglev trains, which float above tracks using magnetic levitation, reducing friction and enabling smoother, faster travel. The advancements made in superconductor technology for fusion may also accelerate improvements in these areas, creating a ripple effect across industries. As research progresses, the integration of superconductors promises to revolutionize how we generate, transmit, and utilize energy across multiple facets of everyday life. The path toward practical fusion energy powered by superconductors is marked by ongoing challenges, including the development of materials that can withstand extreme conditions inside reactors while maintaining superconducting properties. Scientists are exploring new high-temperature superconductors that operate at more manageable temperatures, which could simplify cooling requirements and reduce costs. These advancements may lead to more robust and accessible superconducting systems, further integrating them into fusion technology and beyond. The synergy between materials science and energy research continues to inspire optimism for a future where superconductors play a foundational role in meeting humanity's growing energy needs sustainably and responsibly. In the realm of superconductors, the journey from theoretical discovery to practical application is a complex and multifaceted endeavor that benefits greatly from international cooperation. Researchers from diverse scientific backgrounds and geographical regions join forces, sharing insights and experimental data that accelerate progress. This collaborative spirit is essential because the challenges faced, such as understanding the microscopic mechanisms behind superconductivity and developing materials that perform reliably at higher temperatures, are deeply intricate and require a pooling of intellectual and technological resources. Institutions across the globe participate in coordinated projects, fostering a dynamic environment where breakthroughs in one laboratory can quickly inform and inspire innovations elsewhere. Such collective efforts not only enhance the pace of discovery, but also help standardize methodologies and materials, which is crucial for scaling superconducting technologies from laboratory curiosities to industrial realities. Beyond the scientific laboratories, international partnerships extend into the realm of large-scale infrastructure and engineering projects, where superconductors hold immense promise. For instance, the construction of next-generation particle accelerators, advanced medical imaging devices, and highly efficient power grids increasingly depends on superconducting components developed through multinational collaborations. These projects often require the expertise of physicists, engineers, and materials scientists working in concert with policymakers and industry leaders. Through shared funding and resource allocation, countries can undertake more ambitious initiatives than would be possible individually, spreading the risk and multiplying the potential benefits. Moreover, global collaborations facilitate the cross-pollination of ideas, allowing best practices to emerge and be adopted worldwide, thus accelerating the deployment of technologies that can revolutionize energy transmission, transportation, and healthcare. A particularly inspiring aspect of international cooperation in superconducting research is the establishment of open access databases and collaborative platforms where experimental findings are made available to the global community. This transparency nurtures a culture of openness and reproducibility, essential for scientific integrity and innovation. Researchers can build upon each other's work without unnecessary duplication, optimizing the use of time and funding. In addition, global conferences and workshops provide critical venues for dialogue, enabling experts to discuss challenges, hypothesize new approaches, and align their efforts towards shared goals. Such gatherings often spark interdisciplinary partnerships that bridge gaps between theoretical physics, materials engineering, and applied technology, bringing superconductors closer to widespread practical use. This interconnected approach exemplifies how the scientific community transcends borders to tackle some of the most demanding questions in modern science. Importantly, the collaborative momentum surrounding superconductors also contributes to the training and development of the next generation of scientists and engineers. Exchange programs, joint research projects, and international fellowships provide invaluable opportunities for young researchers to gain hands-on experience and broaden their perspectives. These programs cultivate a global network of experts who are well-versed in both the theoretical foundations and practical challenges of superconducting materials and devices. As these emerging professionals bring fresh ideas and innovative techniques to the field, they help sustain a vibrant research ecosystem capable of adapting to evolving scientific and technological demands. This continuous infusion of talent and knowledge is vital for maintaining the forward trajectory of superconducting research on the world stage. As these collaborative efforts advance, they pave the way for new superconducting technologies that can integrate seamlessly into everyday life, transforming industries and enhancing sustainability. The shared vision among international partners is one where superconductors are no longer confined to specialized applications, but become foundational components in energy systems, transportation networks, and medical devices. This global synergy nurtures an environment ripe for innovation, where theoretical insights swiftly translate into tangible solutions that address pressing challenges. With each cooperative milestone, the horizon of what superconductors can achieve expands, inviting continued exploration and discovery. Superconductors represent a fascinating frontier in material science, offering extraordinary electrical properties that challenge conventional limits. These materials, capable of conducting electricity without resistance below certain critical temperatures, open doors to revolutionary advancements. Theoretically, Superconductors enable lossless energy transmission, which could drastically reduce the inefficiencies that currently plague power grids worldwide. Such a breakthrough would not only conserve vast amounts of energy, but also support the growing demand for sustainable infrastructure. In transportation, superconducting magnets hold the promise of levitating trains at high speeds with minimal friction, potentially transforming how people and goods move across distances. Beyond these, the quantum mechanical phenomena underpinning superconductivity fuel innovations in computing, where superconducting qubits may offer unprecedented processing power and speed. These theoretical applications illustrate the profound impact superconductors could have, not only in enhancing existing technologies, but also in spawning entirely new fields of research and industry. Practically, the journey from laboratory discovery to real-world application is well underway, with superconductors already playing pivotal roles in several advanced technologies. Magnetic resonance imaging, or MRI machines, rely heavily on superconducting magnets to generate strong and stable magnetic fields, essential for detailed internal imaging. This medical application alone has transformed diagnostics, enabling non-invasive insights that save countless lives. In energy sectors, superconducting cables and fault current limiters are being tested and implemented to improve grid stability and efficiency, reducing power losses and enhancing safety. Moreover, particle accelerators, such as those used in cutting-edge physics research, depend on superconducting magnets to steer and accelerate particles to near light speeds, deepening our understanding of the universe. These practical uses demonstrate how superconductors, despite their complex requirements, are steadily becoming integral to critical systems. As manufacturing techniques improve and materials become more robust and affordable, the scale and scope of these applications are set to expand, bringing superconducting technology from niche domains into broader societal use. Looking forward, the promise of high-temperature superconductors remains one of the most exciting prospects in this field. Achieving superconductivity at temperatures closer to ambient conditions could eliminate the need for costly cooling systems, making these materials far more accessible and practical for everyday applications. Such advancements could lead to widespread adoption in urban power grids, enabling smart cities powered by efficient, resilient electrical networks. Transportation systems might benefit from more affordable and reliable maglev trains, reducing environmental impact while improving travel times. Additionally, the integration of superconducting components in renewable energy technologies such as wind turbines and energy storage devices could enhance performance and durability, accelerating the transition to cleaner energy sources. With ongoing research dedicated to understanding and manipulating the quantum behaviors that govern superconductivity, the horizon is rich with potential for breakthroughs that could redefine technological capabilities on a global scale. The collaborative spirit that drives superconducting research today embodies a shared hope for harnessing these extraordinary materials to meet humanity's evolving needs. International partnerships pool expertise and resources, accelerating the pace at which theoretical models translate into practical innovation. This synergy encourages experimentation with novel materials, new fabrication techniques, and creative engineering solutions that overcome existing challenges. As a result, the landscape of superconducting applications continues to diversify, encompassing fields as varied as medical technology, sustainable energy, quantum computing, and advanced transportation. Each incremental advance contributes to a cumulative momentum, fostering optimism for a future where superconductors are seamlessly integrated into daily life, enhancing efficiency, reliability, and environmental stewardship. This ongoing evolution invites us to imagine the untapped possibilities that remain, inspiring continuous inquiry and exploration at the intersection of science and society. As we look toward the horizon of scientific discovery, superconductors stand as a beacon of remarkable potential and profound mystery. Their unique ability to conduct electricity without resistance opens doors to a world where energy loss becomes a relic of the past, enabling power grids far more efficient than those we rely on today. Imagine a future where electricity flows seamlessly across continents, reducing waste and supporting cleaner, more resilient energy systems. Beyond power transmission, superconductors promise transformative advances in transportation, where maglev trains glide silently at incredible speeds, redefining travel as we know it. These theoretical visions are not mere dreams. They are steadily becoming tangible goals through sustained research and innovation. Each step forward in understanding these materials brings us closer to integrating them into everyday life, inspiring us to imagine the countless ways they could reshape our world. The realm of computing offers another fascinating frontier for superconductors. Quantum computers, powered by superconducting circuits, hold the promise of solving problems once thought insurmountable, from complex molecular simulations to optimization challenges in logistics and cryptography. Such machines could revolutionize medicine, finance, and artificial intelligence, unlocking insights hidden within vast data landscapes. In medical technology, superconducting magnets form the heart of MRI machines, producing detailed images that save lives with non-invasive diagnostics. Future improvements in superconductor materials may lead to more compact, affordable, and accessible healthcare devices, broadening the reach of advanced medical care. These applications exemplify how the theoretical properties of superconductors translate into practical tools that enhance human well-being. They remind us that the pursuit of knowledge is intimately tied to the betterment of society, fostering a deeper appreciation for the interplay between science and daily experience. Despite the extraordinary promise, the path to widespread adoption of superconductors is marked by challenges that inspire creativity and perseverance. The necessity of extremely low temperatures for most superconducting materials requires sophisticated cooling systems, which can be costly and complex to maintain. Researchers are actively exploring new compounds that exhibit superconductivity at higher temperatures, a breakthrough that would significantly ease practical implementation. Advances in material science, nanotechnology, and engineering are converging to address these obstacles, driving a vibrant field of interdisciplinary collaboration. This ongoing journey reflects the resilience of the scientific community, which embraces uncertainty as an invitation to innovate. Every experiment, every theoretical insight, and every prototype contributes to a growing foundation upon which future technologies will be built. Encouraging curiosity and support for superconductor research invites each of us to become participants in the unfolding narrative of technological revolution. Whether through education, advocacy, or simply nurturing a sense of wonder, our collective engagement helps sustain the momentum that transforms laboratory discoveries into societal benefits. The story of superconductors is not only one of atoms and electrons, but also of human aspiration and collaboration. It reflects a shared journey toward a future where the invisible forces of physics serve to elevate our quality of life, protect our planet, and expand the horizons of possibility. By embracing this journey, we contribute to a legacy of exploration that inspires generations to come. In closing, the exploration of superconductors embodies the spirit of science as an ever-evolving quest for understanding and improvement. Their extraordinary properties challenge us to rethink what is possible, inviting patience and persistence amid complexity. As we stand at this threshold, it is the collective curiosity and determination of researchers, innovators, and observers alike that will illuminate the path forward. Together, we hold the promise of transforming these remarkable materials from scientific marvels into cornerstones of a sustainable and interconnected future. Let us carry this vision gently in our minds, nurturing hope and inspiration as we await the discoveries yet to come. The journey ahead is as vast as it is exciting, and we are all invited to be part of it.